In rolling, as we have discussed that maximum reduction delta H, maximum reduction in thickness of the sheet, delta H max equal to R tan square alpha. This maximum reduction happens when alpha equal to beta. So we know that alpha equal to angle of bite. Similarly, what is beta? Beta equal to friction angle. So whenever the angle of bite is equal to angle of friction, which is based on Coulomb law of friction, Coulomb friction condition, delta H equal to, substitute alpha equal to beta tan square beta. So as we know that tan square beta is nothing but mu square. Delta H max equal to R mu square, where mu equal to tan beta. Mu is coefficient of friction. So if you want to increase the reduction, so what you need to do? You need to increase the radius of the roller or increase the friction between the rollers and the sheet. It is called maximum possible reduction or maximum draft equal to delta H max. So reduction increases with increase in the radius and increase in the, because maximum reduction is directly proportional to the radius of the roller and coefficient of friction between the roller and the sheet. So it increases, maximum reduction increases with increase in the radius and the coefficient of friction. In the same way, how is the variation of pressure and velocity along the while the strip is moving from entry point to the exit point? If you draw the diagram, so velocity at the entry point, this one is exit point and here it is neutral point. So this side is called lagging zone. So if you take this area, take A, B, C, D, take that out. So A, B, C, D, and this is neutral axis. So velocity at the entry point, A is entry point, B is exit point, so here we can give E and F. E and F is neutral axis. So at entry point, the velocity, actually we talk here relative velocity. If you draw the diagram, relative velocity is maximum and this one is pressure. Okay, so this line is pressure, pressure developed between roller and sheet. So the points here is A, E, B. A is entry point, B is exit point, E is neutral point. So sorry, this is actually has to be like this. So diagram is slightly deviated. So this point, at entry point, pressure is 0, and as you know, the strip enters into the between the rollers, the pressure increases. At the neutral point, pressure will be maximum. This is P max. At neutral point, pressure is maximum, and pressure will be 0 again at exit point. Similarly, relative velocity, this one is V minus V naught, V1 minus V. What is V and V naught? So V is velocity of rollers, V naught is velocity of strip at entrance, at entry point. V1 is velocity of strip at exit point. This is V1. So V minus V naught is relative velocity at entry. So similarly, this region is called lagging zone. You can say lagging zone. Lagging zone. This region is called, from neutral point to exit point, leading zone. Difference. So lagging zone and leading zone. In lagging zone, the pressure increases, and in leading zone, the pressure decreases from neutral point to exit point. And relative velocity is 0 at neutral point. And thus, if you look at this, difference between the velocities, that is called slip. Difference between the velocity of the strip and velocity of the roller is called slip. Forward slip is the relative velocity of exit from neutral point to exit point is called forward slip, and from entry point to neutral point is called backward slip. Similar to this, there is important formula here. Pressure developed is P average equal to average pressure in rolling. This is average value. Power or energy required to run the rollers. Power or energy required to run the rollers. Power equal to POWR. Power P equal to, normal formula is torque into omega. Torque is, omega is constant, where omega equal to angular velocity, so which is nothing but 2 pi n. Omega into torque. Torque is nothing but force into radius. So here radius is, we have to take as length of the contact. It is actually considered as A. So omega into force into A, where F equal to roller separating force. A is arm factor, so moment arm. A is the moment arm. A is moment arm. Arm moment arm. A equal to lambda L. Lambda is constant, which is called arm factor. They will give the constant value for each material, varies from 0.3 to 0.4. L is the length of the deformation zone. So omega into force into A is nothing but lambda L. L equal to, if you remember that, L equal to R delta root R delta H, length of deformation zone. So power equal to omega is nothing but 2 pi n into force, you can write it as P max, pressure into area is projected area, into lambda L. So power equal to 2 pi n into P max into projected area is nothing but B into L into lambda L. So where B is width of the strip, so 2 pi n into P average, sorry, not it is not max, P average, sorry, 1 second, P average, because we won't take P max, or we take P average. P average into B is width into length into delta lambda L. Substitute L equal to R delta H. So final formula for power equal to 2 pi n into P average into B into lambda L square is nothing but R delta L equal to R delta H. L square equal to R delta H, because L is nothing but root R delta H, length of deformation zone. So L square is R delta H. Power is generated is the energy required to run the rollers for rolling is depending upon the radius of the rollers, length of the deformation zone, and as well as width anyway constant, arm factor. Even you can substitute delta H, you can substitute with instead of pressure, sometimes they give shear yield stress. Or this can be written as power equal to 2 pi n into yield stress into B lambda or delta H. So pressure also is force by area, stress also force by area. Sometimes they give the pressure developed, sometimes they give indirectly stress developed or yield stress, because its rolling is a plastic deformation and it is a forming process. So it has to be minimum yield stress and maximum less than the ultimate stress. So they give minimum yield stress. So this is the final formula for power required for rollers. And in the same manner, if you want to find out the force required for roller separating force, so here we have given power required for one roller. Power required for two rollers is 2 into power required for one roller. So multiply with 2. So for two rollers, so we have to multiply with 2. Power required for moving two rollers. So to reduce roller separating force or power required, force equal to area, stress into area, to reduce the roller separating force, why we need to reduce is, if there is more force is developed, more force or more stress is developing between the roller and the strip, then there may be failure of the shafts. To avoid the failure of the shafts, to avoid failure of shafts in rolling, we need to reduce roller separating force. F equal to yield stress into area is nothing but projected area. B into L. L is nothing but root or delta H. So here, if you want to reduce the roller supplement, reduce the radius or reduce yield stress. Yield stress can be reduced. Roller separating force is reduced by following methods. First one, reduce yield stress by heating the strip. The metal strip which is undergoing rolling operation, we have to heat that metal strip, then yield stress generated has to be it will come down. If you heat the material, yield point will come down. That means yield stress developed to come down. Roller radius. So that is nothing but reduce the size of the rollers. Size of the rollers, you can, how much you have to reduce, that we will discuss in the next topic. And you can use back tension, backward direction. If you are forward force and backward force, back tension, both stress, if you pull from both sides, that will also reduce the roller separating force. So these are the different methods to reduce the roller separating force, the force generated between the rollers and the strip. Use back tension and front tension. So to understand this, suppose this is a rolling strip. So here this one is this direction. Sigma 1 is front tension, sigma 2 is back tension. So you are pulling in opposite directions. So if you pull that one, obviously that will also reduce the force generated between the roller and the strip. Sigma 1 equal to front tension, sigma 2 is back tension. Next topic is types of rolling mills. So why do we need to go for rolling mills? So there are different applications why we need to go for this is. First one is too high rolling mill. Normal rolling mill is also called, if there are only two rollers, that is called too high rolling mill. only two rollers will be present. Two high rolling mill. Next one is three high rolling mill. To increase the reduction, there is less space, then we go for three high rolling mill. Next one is four high rolling mill. Another one is four high is backup rollers will be there. Four high rolling mill or backup rolling mill. In this, as we have discussed that roller separating force can be reduced by reducing the roller diameter. So here we use smaller rollers such that the force generated or stress developed will be less. If you use smaller rollers, we need to use small shaft. If you use small shaft, there is a possibility of breaking the shaft. If there is a shaft failure may be there. So to avoid that, we use supporting rollers. This layout diagram. Small roller, one small roller, here supporting roller. To support this roller, we use another big roller. This one rotation is opposite. If it is rotating anti-clockwise, this one rotates clockwise. This is rotating anti-clockwise, this rotates clockwise. Sorry, yeah. Power is given to smaller rollers, so bigger rollers, but shaft won't, to avoid the shaft failure, this we use. To avoid shaft failure while using small rollers. Next, fourth one is cluster rolling mill. Same concept, instead of one supporting roller, if we use two supporting rollers for each roller. Cluster rolling mill. Two supporting rollers for each roller. Next, fifth one is planetary rolling mill. In this is entirely different from the earlier ones. Here smaller rollers are fixed to the one big roller. Maximum reduction takes place in this. So the smaller rollers, these are called cluster rolling mill. Maximum reduction takes place due to small size of the rollers. So this is about rolling. Next topic is drawing. So before going to this topic, we will do at least two problems from the old GATE questions. GATE question number 20. Question number 20, one more question. GATE 2002. Hot rolling of mild steel is carried out. Question is hot rolling of mild steel is carried out options are at recrystallization temperature, below recrystallization temperature, between 100 to 150. Sorry, A is at recrystallization temperature, B is between 100 to 150, C is below recrystallization temperature, D is above recrystallization temperature. Here he has mentioned hot rolling. So it is hot rolling means hot working operation. So hot working operation takes place above recrystallization temperature. So option satisfies is D. Carried out above recrystallization temperature. So answer is D. Simple one mark question. Question number 16. GATE 2003. Cold working of steel is defined as working at its recrystallization temperature, above its recrystallization temperature, C is below recrystallization temperature, D is at 2/3 of the melting point of the steel. So cold working is, as we know that cold working is any mechanical operation takes place below recrystallization temperature is called cold working. So option satisfies is C. Cold working of steel is defined as working below recrystallization temperature. Working below recrystallization temperature. So this is cold working, hot working, very important. What I mean, temperature, simple question only, so many times they asked, not only in GATE, so many other public sector exams you will find this question. And otherwise they can ask mechanical properties, what will happen to the strength, hardness, brittleness. So next question, 14th question. Two marks question. Question number 14. GATE 2004. Two marks question. In a rolling process, sheet of 25 mm thickness is rolled to 20 mm thickness. Roll is of diameter 600 mm and if rotates at 100 rpm, the roll strip contact length will be. So he has given thickness of 25 mm, initial thickness. So H0, initial thickness, equal to 25 mm. H1, final thickness, equal to 20 mm. Roller diameter, equal to 600 mm. And speed of the roller, he is asking roll strip contact length. So to calculate roll strip contact length, equal to r theta. As we know that if you draw the diagram, so this one is roller, this part roll strip contact length is, if this is A, point A, and this one is B, AB is called roll strip contact length. In the length, of the arc between entry point and exit point, or theta, alpha, sorry, not theta, or alpha. Alpha is angle of bite. Roll strip contact length equal to R alpha. R we know that 300 mm. Alpha equal to, so to get alpha, what we need to do, he has given initial diameter, final diameter, delta H equal to tan square alpha mu square r. There is one formula which is nothing but delta h equal to angle of bite is equal to tan inverse alpha equal to, you need to calculate. So delta h equal to tan square alpha into r. Alpha equal to square root of delta h by r. Substitute delta h is nothing but 5 mm divided by r is 300 mm, square root of. Substitute the value and you will get in radians 0.129 radians into pi by 180. You have to multiply. Roll strip contact length equal to r alpha equal to r is 300 mm into 0.129 is equal to 38.72 mm. So 2 marks question. If you know the formulas, then you can solve in just few seconds, in 1 minute, because you have, for each question you have 3 minutes, you can easily solve. Question number 9. Gate 2006. A 4 mm thick sheet is rolled with 300 mm diameter rolls to reduce thickness without any change in its width. The frictional coefficient at the work roller interface is 0.1 mm. The minimum possible thickness of the sheet that can be produced in a single pass. So he has mentioned initial thickness. Of sheet equal to 4 mm, which is nothing but h naught. Diameter of the rollers d is equal to 300 mm. Coefficient of friction at roller and work interface mu equal to how much? 0.1. Minimum possible thickness of the sheet is produced. It is indirectly saying maximum possible reduction happens. That